you can carry on with the main talk.
Okay, great. I'm a little worried I can't go backwards for some reason, so whatever, I guess in life we always just move forward. But in any case, so thanks very much to the organizers for giving me the opportunity to share some of the things that I've been thinking about. Today, I'd like to tell you about,
Brandon, just interrupt you very quickly, sorry. Please feel free to unmute yourself and ask questions at any point in the talk. Thank you. Sorry, Brandon.
Yeah, please, that'd be great. Right, so today I'd like to tell you about some work that was done in collaboration with these wonderful physicists. There's Jin-Byun Bae, Jeff Harvey, Sung-Jae Lee, and Kim-Young Lee. To the extent that I say anything interesting today, the credit goes to them, and to the extent that I say anything that offends your scientific sensibilities, the blame almost certainly lies with me. So as I was just saying, the one sentence summary of our paper is that we were interested in finding physical models in which exceptional finite symmetry structures arise. And it'll turn out that we'll be able to construct such models by playing games with the Monstrous CFT. So we'll be trying to add a few new pages to the already very rich and beautiful story of Monstrous moonshine. But before I get into the details of these games, I wanted to start with some light mathematical reminders, which hopefully will also serve to motivate our constructions. So we'll start with finite groups. Perhaps the first observation to make is that despite being in some sense more elementary objects than their continuous cousins, finite groups are far more difficult to study. And I flashed a bit of history here to try to convince you of that. For example, as you can see, the semi-simple complex Lie algebras were classified almost entirely by killing, with a few improvements made by Cartan and Dinkin. And this happened within the span of a few years, over 100 years ago. On the other hand, when it comes to the classification of finite simple groups, I didn't really know where to start the history, but Wikipedia suggests that the history starts in 1832. And since then, it's the proof of the classification has taken up tens of thousands of pages and hundreds of mathematicians with the help of modern computers. And even then, the verification to some extent is still ongoing for this theorem. So anyways, it's truly one of the most remarkable theorems of modern mathematics, and one that I think that math nerds should be more evangelical about. So today I'll try to do my part in spreading that gospel. Anyways, here's a pictorial representation of the classification theorem. Roughly speaking, it says that any finite simple group either belongs to one of 3 infinite families or else is one of 26 exceptional cases, which are often referred to as the sporadic groups. So for example, one family is the cyclic groups of prime order, which are shown, I can't really see my mouse here, but they're shown on the very rightmost column. Another family is the alternating groups of degree at least 5. Those are shown on the very left. And the third infinite family is a sort of catch-all family, and roughly speaking, it corresponds to groups that you would obtain by considering Lie groups over finite fields. And then, of course, there's the monster group, which is the largest one, and 25 other exceptional cases called the sporadic groups, which are indicated down at the bottom in green. Great. So as I alluded to in my elevator pitch, one of the intriguing aspects of these exceptional groups is that 20 of them appear in some way or another inside the monster group as subquotients. And in fact, more generally, they participate in a very interconnected web with one another that is visualized in this diagram. Staring at this picture was sort of one of the many inspirations for our project. For example, one of our goals was to see these arrows explicitly appear in a physical construction. And so I hope to argue to you today that we were at least partially successful. Now, of course, since group theory is the abstraction of the study of symmetry, each finite simple group ought to be the symmetry group of some kind of natural object. One example is this group A5, which is the simplest non-trivial finite simple group. it's the symmetry group of the dodecahedron. And likewise, you can try to develop a similar story for the rest of the sporadic groups. It's useful to do so because they're super large. And in fact, I think historically, the only way several of the sporadic groups were even proven to exist in the first place is by exhibiting them as the automorphism groups of other mathematical structures. So let me give you some examples. The monster group, which in all of my talks is played by Monstro the whale from Pinocchio, furnishes the symmetries of a rather large algebra called the Grice algebra, which in addition to the usual algebra product also admits an inner product. And the statement here is just that the monster group preserves both of these structures. Another example of a sporadic group is the Mathieu group, which I think will definitely appear in later talks in this conference. It was first discovered in connection with classical error correcting codes, and specifically the extended the Golay code. And one final example that is quite dear to my heart is the Thompson group, which you may hear about in a later talk by Jeff Harvey. And it was first discovered as the symmetry group of a 248-dimensional even unimodular lattice. Now, from what I've just told you, it seems like each different exceptional group requires us to consider objects from very different corners of the mathematical universe. But the program of Moonshine, using ideas from physics, offers a somewhat more unified picture of some of these results, and in the process endows them with some extra structure. So, for example, we can start by revisiting the case of the monster group. It's a cherished result of mathematical physics that it describes the symmetries of a meromorphic conformal field theory with central charge 24. And you can ask whether or not the Grice algebra that I described on the previous page arises in some way in this physical theory. And the answer is that it does. And to see it, well, what you do is you just restrict your attention to the space of dimension 2 operators of the theory. There's 196,884 of those, which is the same dimension as the Grice algebra. And what the Grice algebra is doing for you is it's essentially encoding the operator product expansion of the dimension 2 operators. So for example, the inner product tells you something about the leading coefficient in the OPE, and the Grice algebra product tells you about another OPE coefficient. So if you'd like, you can think of the monster CFT as a sort of massive infinite dimensional uplift of the Grice algebra that I described on the previous slide, or 2 slides ago. Moving on to the Mathieu group, an observation which goes back to Iguchi, Uguri, and Tachikawa is that it controls the elliptic genus of K3, which in a physics picture is counting the supersymmetric or BPS states of sigma models into K3. Now, you might want to say, or try to say, an analogy with the case of the monster, that there's some point in the moduli space of K3 sigma models which has M24 symmetry, but there's a very beautiful no-go theorem by Gabardine, Hohenegger, and Volpato, which shows that there's no point in the moduli space of K3 sigma models which admits an action of M24 that preserves the full supersymmetry algebra. So a story analogous to the one in Monstrous Moonshine can't really go through in the same exact way. But nonetheless, the hope is that because M24 arises in the elliptic genus, that it's in some way organizing the BPS sectors of these theories. But making these words precise is still an open challenge, which, if I'm not mistaken, we'll hear a little bit more about later on in this conference. In any case, the Golay code, which I discussed on a previous slide, arises here in connection with the Ramon ground states, but in a way that is probably too complicated for me to attempt to summarize in words. So I refer you to a recent very nice paper of Jeff Harvey and Greg Moore, which goes over this in detail. And finally, as you may hear in a talk by Jeff, there's a sort of analog of Mathieu moonshine, but where the role of the Mathieu group, M24, is played by the Thompson group. Here, we don't quite have a physical construction, but we have a collection of modular forms, which is a sort of, well, depending, it could be thought of as a telltale signature that there's some kind of vertex algebraic construction that, for lack of a better word, categorifies these functions. So the explicit construction of that theory is still an open problem, but even just at the level of these collections of modular forms, the 248 dimensional lattice representation is visible, for example, as the constant coefficient. Okay, so while each of these constructions is very nice in its own right, if your desire in life, as I declared ours to be, is to try to understand the diagram of simple sporadic groups emerge in physics, then they have a potential shortcoming, which is just that, for example, while the Mathieu group, say, appears inside of the monster, their corresponding physical models have not much to do with one another. For example, it's not clear what K3 sigma models have to do with the monster CFT. So this may not be the best starting point for understanding the relationships between sporadic groups from a physics point of view. So the basic starting point of our paper is to offer a different set of physical models, which will have exceptional symmetry groups as their symmetries. And we want to construct these physical models so that they make manifest the relationships between the different sporadic groups. And before giving you the details of how this construction goes, I'll just give you a bird's eye overview of the strategy and the results that it leads to. So this is, again, another slide from my elevator pitch. So our strategy is that we'll take the monster CFT, we'll prune off various chiral subalgebras using the method of Cosets, or if you're a mathematician, you would call this the method of taking commutants subalgebras. And which Cosets we'll take will be distinguished by very natural symmetry considerations that I'll elaborate on throughout the course of the talk. But in any case, the structure that will be led to is a web of chiral algebras, one for each node in this graph, with three main properties. The first property is that, of course, as we demand, the chiral algebra associated to a group G will have G as its inner automorphism group. The second is that the assignment of chiral algebras to groups will be sort of functorial, in the sense that if one group includes into another as a subquotient, then the chiral algebras will include into one another as well. And a further upshot is that several of these groups in this diagram are sporadic. So we'll achieve our goal of finding exceptional finite symmetry structures in physics.
Sorry, Brandon.
Yeah.
Quick question. You just mentioned something about, I didn't catch the full statement. The Mathieu group is inside the monster group, and therefore something doesn't go through. I mean, you said something of this nature.
Yeah, I was just, so I gave these earlier examples of constructions of physical models that realize both the monster group and the Mathieu group as their symmetries. So in the case of the monster, it's the monster CFT. In the case of the Mathieu group, it's K3 sigma models, supposedly. And I was just saying that, like, you know, we wanted to look at, like, our starting point, our mathematical motivation is this diagram. And as you can see from this diagram, there's an arrow from the group M24 to the monster. And so we know that the groups are related in some way. And we want to understand this relationship from physics, but it's not obvious how we would do that if we took the monster CFT and K3 sigma models as our starting point, because they don't really have anything to do with each other. So we're going to offer different models, basically.
But philosophically speaking, would there not be a way, because there is, I mean, Daniel, Passion, Volpato, and Natalie wrote this paper about trying to understand the monster CFT, the monster group as being a symmetry of certain BPS states, right?
You mean in like this heterotic monster?
In heterotic construction, right? So analogously, would you not just say that, like, just look at BPS states of various string theories, or?
Yeah, it's true that that's right. There is a heterotic interpretation of the monster group, but again, that heterotic string model, other than having supersymmetric states, doesn't have anything obvious to do with the
with K3, I mean.
with K3 sigma models. Yeah.
Okay, that's what.
Whereas
Okay.
these Chiral algebras that we construct are different in that literally, for example, the Chiral algebra that we associate to the Thompson group will be sitting literally inside the monster CFT. So they're very much related.
Okay.
This is actually a good time for other questions because I'm going to start to get into details. So that was sort of the end of my philosophical hand waving. Okay, I've gotten to 5 Mississippis in my head, so we move on. Great. So now I'll start to get into a few more details of this construction, but I should first start by clarifying certain terminology because even though mathematicians and physicists have sort of been studying the same thing for many decades, there's not much communication between the fields. So let me go over some generalities of what I mean by Chiral algebras. So for a physicist, the natural starting point is 2D conformal field theory, where a special role is played by holomorphic operators. And the words are just that any such holomorphic operator leads to an infinite dimensional symmetry algebra, which is just the one that's spanned by its modes if you expand it in a power series. And furthermore, since the product of holomorphic operators is again holomorphic, the space of such operators forms a consistent truncation of the full operator algebra, and you can study it in its own right. And it's usually a useful starting point that you start with before analyzing the full CFT. So this space of holomorphic operators in a 2D CFT is the thing that I'll call a Chiral algebra. If you're a mathematician, you know this object as a vertex operator algebra. Anyways, once you have the holomorphic and the anti-holomorphic Chiral algebras in hand, you can decompose the Hilbert space, the space of states of the conformal field theory, into representations of their tensor product. For a physicist, the highest weights of these representations are usually called primaries. So I'm just telling you things you already know, but just to establish some terminology. So the next point to make is that every local 2D CFT has such holomorphic operators. In other words, it has a non-empty Chiral algebra. And that's just because every local 2D CFT has a stress tensor. And if you write the conservation and tracelessness of the stress tensor in complex coordinates, then what you'll find is that, for example, the ZZ component of the stress tensor is holomorphic, and the Z bar component of the stress tensor is anti-holomorphic. And the infinite dimensional symmetry algebra that's spanned by its modes is none other than the Virasoro algebra. So in other words, we'll sort of take as a definition that all Chiral algebras will have a Virasoro subalgebra. And the commutation relations of the Virasoro algebra are equivalent using sort of standard CFT arguments to the operator product expansion of the stress tensor with itself, which takes the form that I've indicated at the bottom of the page. And we'll be coming back to this OPE shortly. It'll be a starting point for several of our constructions. So I should give you one more example. Generically, the Virasoro algebra is basically all that there is in a 2D CFT. That's the entire Chiral algebra. But we tend to study very special cases which have more operators in the Chiral algebra. And one example is just that if you have a 2D CFT which has some kind of continuous global symmetry, then by no other's theorem, that theory should be expected to have conserved currents. And in a 2D CFT, those will be dimension 1 operators that belong to the Chiral algebra, and their OP is constrained to take this form here. So for the sake of honesty, I've put in parentheses that Noether's theorem is not actually a theorem. It even admits some counterexamples, but that won't matter at all for anything I have to say. And I should also stress at this point that actually neither the monster CFT nor any of the new models that we construct from it will have dimension 1 operators. So their symmetry groups are going to be entirely discrete and finite, in fact. Okay, so the game that we'll try to play is that we'll take the monster CFT as a sort of seed object, and we'll construct new objects out of it. And we want to study the pattern of symmetries that these new objects inherit from the fact that their parent was the monster CFT. And in 2D CFTs, there's sort of at least 2 common tools that one employs to construct new theories out of old ones. The first is maybe a more familiar one. It's basically the method of taking an orbifold. If you're a physicist, this is just a fancy way of saying that you're gauging a discrete subgroup of the full symmetry group. The subgroup should be non-anomalous, of course. And well, actually, the study of various twisted sectors that arise when you take cyclic orbifolds in the monster goes by the name of generalized moonshine. And I think it's fair to say that by now it's fairly well understood, and it does in fact lead to various interesting generalizations of the sort of classic monstrous moonshine story. But I won't have anything to say about that in this talk. So instead, we'll be using another tool from CFT, which is known as the Cosets method. And it was originally studied in the context of affine Katz-Moody algebras, or current algebras, by Goddard, Kent, and Olive. But as we'll see, it's more general than that. And in particular, we'll be able to put it to good use in the context of the monster CFT. So let me offer a bit of informal intuition about what a coset is. It's a natural strategy in life, I guess, to try to build up something complicated using better understood ingredients. And one very striking example of this is that you can often describe Calabi-Yau sigma models at special points in their moduli spaces by taking a tensor product of supersymmetric minimal models. Supersymmetric minimal models are very well understood. They're rational conformal field theories. And so it's sort of striking that you can obtain these very complicated sigma models using such simple building blocks. Cosets are, in a sense, a way to accomplish the reverse. You start with a complicated theory and you seek to discover its pieces, essentially. But to be more precise, in the context of chiral algebras, what we'll be trying to do is this. We'll be given a chiral algebra V, and we want to discover subalgebras which take a tensor product form. So we want to discover subalgebras of V which take the form W tensor W twiddle. And as a somewhat technical point, I stress that the stress tensor of W tensor W twiddle and V should be the same. So it turns out that it's, if you're trying to play this game, it's often convenient to start by thinking about stress tensors. And the idea is just that almost by definition, if both W and W twiddle are to be chiral algebras, then they should each have their own stress tensors, which I call little t and little t twiddle. And moreover, the sum of their stress tensors should be equal to the stress tensor of the original theory. What I mean when I say that little t and little t twiddle should be stress tensors is just that they should have the canonical OPE of a stress tensor with itself, which I flashed on an earlier slide when I was giving chiral algebra generalities. So the OPE should take this form, But the central charge can be something different. It's a smaller value of the central charge than the central charge of the seed theory. And because W and W twiddle sit as a tensor product inside of V, they both commute with one another. And in particular, the stress tensors, their corresponding stress tensors should commute, which just means that their OPE should be regular. So these last three equations here are the equations that you end up wanting to solve. Okay. And so once you've found a decomposition of the stress tensor of your C theory, you sort of like to construct new theories around the scaffolding. The sort of minimal thing that happens is that T and T twiddle each generate their own copies of the Virasoro algebra. So if V is your original chiral algebra, then at least what you can say is that there's a tensor product of the Virasoro algebra generated by T and the Virasoro algebra generated by T twiddle that sits as a subalgebra inside of V. But in general, there are actually even larger algebras that you can construct around these Virasoro algebras. They're sort of the abstract definition of W, for example, if you like, is that it consists of all the operators in the original seed theory which commute with the stress tensor T twiddle. And likewise, the abstract characterization of W twiddle is that it consists of all the operators of the original theory that commute with T. And so, well, we refer to, W and W twiddle as a commutant pair if they're sort of the largest possible subalgebras that commute with one another and have little t and little t twiddle as their stress tensors. So the strategy will often be to pick a known and tractable subalgebra W, which you feel that you know how to solve, and sort of considering its commutant partner, its dual, if you'd like, W twiddle, which you can think of as being obtained by taking your C theory and just kind of chopping off W. And it turns out that you can reason a lot about the properties of W twiddle just by knowing the fact that it sits as a commutant pair with W inside of the monster CFT, let's say. So it'll be an effective way of reasoning. Okay, so this discussion has been pretty abstract so far. So let me perhaps give it in a context that's at least most familiar to physicists. And I imagine that mathematicians play around with this kind of thing a lot as well. So the idea is that you take your seed theory to be an affine Kac-Moody algebra based on a group G. As I mentioned earlier, such an affine Kac-Moody algebra arises as part of the chiral algebra whenever your 2D CFT has some kind of global symmetry group G. Its stress tensor takes the form, it takes the form that I've written here. It can be expressed in terms of the currents of the global symmetry. And it turns out that you can locate other stress tensors in this theory, little t, basically by picking a subgroup H. So if you pick a subgroup H and you construct its corresponding Sugawara stress tensor out of the currents that lie only in H, then you can just compute that little t has the OP of a stress tensor, and so does big T minus little t. So if you'd like, you can construct cosets around this scaffolding, and you often get an interesting theory, W twiddle, by taking the coset of one larger affine Kac-Moody algebra by a smaller one. So just to give you one concrete example, if you take an affine Kac-Moody algebra based off SU2 times SU2, I haven't told you what the level means, but for those of you who know, you take an affine Kac-Moody algebra of level K, tensor an affine Kac-Moody algebra of level 1, both SU2, and you consider the diagonal SU2 that sits inside of it, which has level K plus 1. And if you consider that coset then what you obtain is the kth minimal model. So for k equals 1, you get the icing model. For k equals 2, you get this like 3-state Potts model, or Z3 parafermion theory, and so on and so forth. Okay, so as I said, the monster CFT has no currents, so we can't apply the literal GKO coset method to it directly, but the same sort of idea applies.
Hey, brother, quick question.
Yes.
This previous slide.
Mm-hmm.
You want W and W twiddle to be commutant pairs, right?
Mm-hmm.
Do you have to impose extra constraints on that, or is it just obvious how to get it?
It's not. I've sort of just, well, so the minimal ingredient that you sort of need to be able to construct W and W twiddle is like this pair of stress tensors that I was telling you about. So it actually, well, most of what I tell you follows from the fact that if you just compute out what the OP of little t is with itself, then it has the form of the OP of the stress tensor. And so does its complement t minus little t, and they commute with one another. So once you have that, you actually know that like a coset exists or whatever. And well, there's further work you have to do to identify precisely what that coset is. But for example, in this case that I've illustrated for you, the fact that, well, yeah, I'll just say if you compute the OP of T twiddle with itself, then that encodes the central charge. And you discover that the central charge of that thing is the central charge of a minimal model. And there's only sort of one chiral algebra at the values of the central charge that the minimal models have. And it's just the minimal models are all there is. So you automatically know that you get the minimal models out of this construction just by computing the central charge. In general, you have to do a little more work to figure out exactly what the structure of the coset is, but yeah. Are there any other questions? Okay. So, right, we want to apply this technique to the monster CFT. One problem that you run into is that Monstro is a very hungry whale. It eats a lot of stress tensors for breakfast. And so correspondingly, there's a kind of dizzying number of different sub-VUAs with respect to which you could consider taking cosets. The rough intuition for why this is just that, you know, its space of dimension 2 operators is very large. It has dimension 196,884. And so there are a lot of opportunities for certain elements of that space to have the canonical stress tensor OPE. And so, well, instead of trying to compute all of these, we should think a little bit about what should distinguish the kinds of cosets that we're after. And the basic idea will just be that, you know, we're playing this game in the first place to discover chiral algebras with interesting symmetry groups. So we'll privilege certain cosets over other ones based on how much symmetry they preserve. And okay, so now I'll try to be a little bit more precise by what I mean by that. And for this, I have to take 2 more slides to tell you about how symmetries play with taking cosets. Maybe I should stop one more time to see if there are any questions about where we're going or what I've said so far. Okay. So as a tiny preliminary, let me remind you that as we discussed earlier, the Hilbert space of a 2D CFT decomposes into representations of the tensor product of the holomorphic chiral algebra with the anti-holomorphic chiral algebra. And an analogy with this, if you're able to locate a commutant pair, W and W twiddle, inside of V, then V itself decomposes into representations of the tensor product of W with W twiddle. The one interesting feature that arises in the context of the monster is that the form of this decomposition is actually constrained in a sure while-like fashion, in the sense that because W and W twiddle are commutant pairs, it turns out that this implies that I should say the each irreducible representation of W and W twiddle can arise at most once in this decomposition. So it's sort of like I guess it's often referred to as a multiplicity one result. This kind of phenomenon is very common when you consider like the representation theory of dual pairs and things like that. So this is a sort of VOA analog of that. Okay, so I just copied and pasted that decomposition from the previous page. And with that decomposition in hand, it'll be easier for me to tell you what symmetries W and W twiddle inherit from the monster. So the statement is just that the symmetries that W inherit from the monster are precisely those symmetries that can be factorized into this form that I've written here. The rough intuition for this is just that you should imagine that such an X sort of shuffles around the states of W and its representations, but stabilizes the states of W twiddle and its representations. And so you can think of it as a symmetry of just W. And likewise, well, the symmetries that W twiddle inherits from the monster are just those symmetries which kind of factorize in the opposite fashion. So with all the non-trivial action happening in the second tensor factor. And so, okay, let me call M of W and M of W twiddle the subgroups of the monster which are inherited by W and W twiddle in this way. Another fact that is important is that those two groups will commute with one another inside of the monster. And that's simply because they act non-trivially on different tensor factors. So M of W acts entirely on, the left tensor factor in this decomposition, whereas M of W twiddle acts entirely non-trivially only on the right tensor factor of this decomposition. So the upshot is that anytime you have a commutant pair of VOAs inside of the monster CFT, then the symmetries they preserve are a commuting pair of subgroups of the monster group. So I said earlier that we want to privilege certain cosets over others using symmetries, and I'm now prepared to tell you how we're going to do that. We simply demand that this pair of subgroups preserved by the coset is maximal. Maximal in the sense that you shouldn't be allowed to add extra elements to M of W while still preserving the fact that M of W commutes with M of W twiddle. So in other words, they're sort of as large as they can possibly be while still commuting with one another. Okay, so that's already a sort of natural condition that you might choose to impose. And it'll turn out to vastly restrict the number of cosets that we're allowed to consider. But if you want some further motivation for why this is a sensible thing to ask for, I'll just comment that in general settings, such a pair of commuting subgroups that's maximal in the sense that I just described is referred to as a dual pair. And their study leads to very pretty results in representation theory. Like I'm sure everybody in this conference knows these better than I do, but I'll just give you the names. Sure-While duality and Hausdata's correspondence are two examples of this. And so we may hope to recover interesting phenomena in the context of the monster as well by considering dual pairs of subgroups. The other reason that this is sort of natural is because Norton had actually already studied dual pairs of commuting subgroups in the monster, and he gave them the name Monstralizers. So, well, whenever you run to something that already exists in the math literature, you sort of know that you're a little bit on the right track. So I found this encouraging. And thankfully, Norton has already classified many of the pairs to a large extent. And you're led to this really big table, but this is like pitifully small compared to the total number of commuting pairs of subgroups you have in the monster. So this is a huge improvement already. And I emphasize that if you just stare at various entries in this table, then you realize that almost all the sporadic groups that arise inside of the monster sort of participate in some monstralizer pair. So for example, the second entry has the double cover of the baby monster group and a cyclic group of order 2. The next entry is dihedral group D3, which is isomorphic to S3, and the Thompson group are the dual pair. There's Fisher 24, various Mathieu groups, Fisher 23, various Conway groups, Harada Norton. I'm just reading them as I see them, more Fisher groups, and so on and so forth. So somehow this notion is doing a good job of killing most commuting pairs of subgroups while keeping ones that feature sporadic groups. So it's a good starting point for our with our earlier goal in mind. And so let's formalize our problem. We'll refer to a commutant pair of sub-VOAs inside of the monster CFT as a monstralizing commutant pair if the symmetry groups they preserve is a dual pair of subgroups of the monster group. In other words, if the symmetry groups that they preserve are a monstralizer pair. And if anybody has a better suggestion for a name other than monstralizing commutant pair, it would be very welcome. Okay, so let me just summarize the game that we want to play. We start with the monster CFT as our seed theory. We look for decompositions of the stress tensor into two smaller stress tensors of smaller central charge. This will be the scaffolding around which we'll build cosets. And then we construct the maximal, we construct the commutant pair, W and W twiddle, around these stress tensors. We decompose the monster CFT with respect to the representations of this commutant pair. It's restricted to take this Schur vial-like form. And then we can compute the symmetry groups that are preserved by this decomposition and are inherited by W and W twiddle, which we call the M of W and M of W twiddle. And if we find that a maximal amount of symmetry is preserved in the sense that this commuting pair of subgroups is a monstralizer or is a dual pair, then we call WW twiddle a monstralizing commutant pair and we declare victory because it will have inherited probably these interesting, big, often sporadic subgroups as their symmetry groups. Okay, so that's the summary of the game that we have to play. Are there any questions about what I've said so far?
Yeah, I have a question. Sorry, Masita, go ahead.
I have a question. So how do you carry out the first step in practice? I mean, I agree that if you have the first step, everything else follows. So
yeah, it's you mean the decomposition of the stress tensor?
yeah, that's right. What I would imagine is that one might attempt to start from one of the symmetries W and then try to guess the T and then T tilde as a difference and then going back and forth. Or do you have a more systematic way? Like, let's first literally, as you said in this slide, literally start with T tilde and then identify W. That would be more beautiful. But
yeah, so what we certainly don't do is we don't like take this big 196,884 dimensional space and like literally try to compute OPs in it. That would be absurd. We rely on to a very large extent on theorems that have appeared in the math literature, which I'm actually going to tell you about next in the next slide. So maybe if I don't answer your question to your satisfaction, please ask again in a few minutes.
Right. Brandon, quick question. In the previous slide where you listed the monstralizer pairs.
Yeah. Oh, sorry, over here?
Yeah, yeah. Is that exhaustive or is it because somehow the on-the-nose sporadic groups are missing from this list, right?
What was the last thing you said?
Is this an exhaustive classification or is it just an an example of monstralizing pairs?
It is so it's well, okay, this left column here, which it starts with 71, 47, 31, etc., is the order of the largest prime which divides the group. So it's exhaustive in the sense that Norton computed all monstralizer pairs such that the order of the largest prime which divides the dual pair is greater than or equal to 11. He didn't compute yet the monstralizer pairs for which the order of the largest prime which divides it is less than 11. So the cases like 7, 5, 3, 2, I guess, are still open. But these will be sufficient actually for getting sporadic groups on the nose. I've been skirting something under the rug, which is that you don't inherit exactly, for example, 2.b. The thing you inherit is the quotient of the group by its center. So for example, in the case of 2.b, the actual inner automorphism group is not 2.b, it's 2.b modulo its center, which is just b. So a lot of these monstralizer pairs, once you quotient out by the center of one of the groups, it'll lead to sporadic groups on the nose.
Right. And do you think you can get more sporadic groups if you actually do this classification even more? Or?
Maybe, yeah. There are even sporadic groups that arise here that we haven't yet found physical constructions for, but that I think would be very possible to.
You mean moonshine? Or?
Yeah, like for example, here in the, my mouse isn't working, but in the column with order 17, there's this 7:3 times held group. Held is another sporadic group. And we have ideas about how to construct a coset which realizes a Chiral algebra with held symmetry, but we haven't done it yet. But I'll describe to you the examples that we were successful in working. Certainly not all the examples on this list yet. Okay, so I only have 9 more minutes, so I should rush. So to construct these cosets, I've told you abstractly what characterizes them, but now I have to tell you how to actually find them. And to find them, we'll make use of these theorems from the math literature, which establish a very beautiful connection between the group theory of the monster on the one hand and the structure of some of its stress tensors. And one of those statements is as follows. So I remind you that there are 2 conjugacy classes of involutions in the monster group. One is 2a and the other is called 2b creatively. And the statement is just that there is a one-to-one correspondence between stress tensors of central charge 1/2, which I'm calling Ising vectors, and elements of the monster which belong to the 2a conjugacy class. And to give you some intuition for this theorem, let me just tell you how it arises in, well, how it goes in one direction. So I'll show you why every Ising stress tensor leads to an involution in the monster. The statement is just the following. So if you have an Ising stress tensor, then it leads to a decomposition of the stress tensor of the monster CFT, which takes this shape. And you can construct a commutant pair around it. So one of the members of that commutant pair is just the Ising Chiral algebra, and the other one is some other algebra about which I will tell you in a moment. In any case, once you have the Ising Chiral algebra and this other algebra W twiddle at hand, you know on general grounds that you can decompose the monster CFT into a direct sum of representations of their tensor product, which will take this form. And somewhat famously, the Ising model has a Z2 symmetry of its fusion algebra, which in the present context acts trivially on 2 of its irreducible representations, the one with highest weights 0 and 1/2, and it acts as -1 on the remaining irreducible representation of dimension 116. And So from here, you can extend this Z2 of the icing model to a Z2 of the monster, essentially by specifying that that Z2 acts, I really wish I had my mouse for this, but you use this decomposition on the top line, and you specify that the Z2 acts trivially on every state in the first two summands, and it acts as -1 on every state in the third summand. And so this sort of demonstrates how if you have an icing stress tensor, then you're led to a involution of the monster. And it turns out that the reverse arrow works as well. So let me tell you what the upshot is. The upshot is, let's think about this, this coset W twiddle. And in particular, let's ask about what symmetries it inherits. So whatever symmetries it inherits from the monster should commute with the Z2 that comes from the icing model. This basically follows from the general comments I made about how symmetries play with taking cosets. And a more careful computation, which I don't have time to tell you about today, reveals that it actually inherits every symmetry which commutes with the Z2. In other words, it inherits the entire centralizer of the Z2 inside the monster. And that centralizer is none other than the baby monster, the double cover of the baby monster group. And so what you find is that this coset W twiddle that you obtain when you take the monster CFT and you quotient out by the icing chiral algebra is chiral algebra with baby monster symmetry. And baby monster is one of the 26 sporadic groups. This was first observed by Rayhaun. From our current perspective, we can think of this dual pair, this commutant pair of icing and the baby monster CFT as a sort of CFT uplift of the Monstralizer Z2 and 2.b, which is one of these dual pairs of commuting subgroups in the monster. Okay, so I probably only have time to tell you about one generalization of this story. And the generalization has a sort of cute relationship to this phenomenology, which is known as McKay's correspondence. So I'll quickly try to tell you about that.
Sorry, Brandon.
Yes.
Yeah, you can probably take 10 more minutes because you did get a lot of questions in between.
Okay, so like 5 minutes after?
Yeah.
Okay. So, okay, so the basic idea is this. Consider any two elements, G and H, which are taken from the 2A conjugacy class of the monster. It turns out that their product has at most order 6, and it lies in one of 9 possible conjugacy classes. Its product either lies in 1A, 2A, 3A, 4A, 5A, 6A, 4B. People are blocking the last one. I think it's 2B, but correct me if I am wrong. 2B and 3C. And McKay's observation was essentially that the orders of these conjugacy classes are exactly the Coxeter labels of the E8 Dinkin diagram. So you'll often see those conjugacy classes decorating the E8 Dinkin diagram. I honestly don't fully understand where this correspondence comes from, but I think it's pretty mysterious to everybody. But maybe somebody here has an answer. So right. So the idea is that this correspondence, McKay's correspondence, also classifies for you conjugacy classes of groups which are generated by a pair of 2A elements. So in other words, if I take such a G and H, I know that there's basically 9 possibilities. They're all dihedral groups, and they're labeled by the nodes of the E8 Dinkin diagram, basically. And it turns out that the dihedral group so generated by a pair of 2A elements always participates in a monstralizer, often with a sporadic group as one of the members of the monstralizer. So for example, if you choose G and H so that their product lies in the 3C conjugacy class, then it leads to a dihedral group, D3, which is isomorphic to S3. And the other member of that dual pair is the Thompson sporadic group, which is another sporadic group. And we can sort of easily find CFT uplifts of these monstralizers as follows. So recall from earlier that elements of the 2A conjugacy class are related to Ising subalgebras of the Monstrous CFT, or Ising stress tensors. And so you can ask, what do the dihedral groups correspond to if they're generated by a pair of 2A elements? Well, the natural thing you might guess is that you can consider a chiral algebra, which is generated by the corresponding pair of Ising stress tensors. And indeed, you can show that this chiral algebra, which is generated by a pair of Ising stress tensors, inherits the corresponding dihedral group as its symmetries from the monster, and its coset inherits the centralizer of the dihedral group as its symmetry group. So for example, if you follow this chain of reasoning, then and you apply it to the 3C case, then what you'll find is that the coset of W3C, say, has Thompson symmetry. And so I return to this picture of the E8 Dinkin diagram. And this time I label each of the nodes by the symmetry group of the coset that it leads to. So as you can see, we get a bunch of sporadic groups on the nodes. There's 5 of them that are just straight up sporadic groups: baby monster, all 3 Fisher groups. Oh, sorry, one of the Fisher groups isn't on the slide, but two of the 3 Fisher groups appear here: Harada-Norton and Thompson. And the other groups are either extension of sporadic groups or interesting groups of Lie type. And it turns out that if you generalize beyond just these dihedral examples, there are other examples. And here are the ones that we've managed to cook up so far. When I say cook up, I mean actually do explicit computations, and which I'll show you an example of in a moment. So here, this is just the graph from the beginning of my talk, except this time I've now included the Monstralizer instead of just one of the groups. And again, I stress that the thing that's interesting about these chiral algebras is not just that they realize these Monstralizers as the symmetries that they preserve, but furthermore that, for example, if one pair of groups embeds into each other, then their chiral algebras do as well. So for example, here you can see a red line going from the Thompson monstralizer up to the baby monster monstralizer. And in fact, it's also true that the chiral algebra with Thompson group that we found embeds into the chiral algebra with baby monster symmetry. So this assignment is sort of a functorial assignment, if you like, of the category of distinguished subgroups of the monster to a certain category of sub-VOAs of the monster CFT. And okay, so let me just end my talk by saying that we're able to compute the characters of all of those models. And that's essentially because, I'll just say this in words, because these models arise from a coset, their characters are subject to a very tightly constrained modular bootstrap problem, and one that we can solve pretty readily with 3 different methods. So one method is we can use modular linear differential equations. We can also use Hecke operators, and we can use Rademacher series. All 3 of these work. Rademacher works in all cases. These first 2, well, they only work in some cases so far. But okay, so the classic thing that you do in Moonshine is you compute the characters and you show that indeed they decompose into representations of the proposed symmetry group. So I'll end my talk by showing this this vector valued modular form that we were able to compute. And well, we claim that this is the characters of the Thompson CFT that we found. And as you can see, for example, the leading coefficients in each component are precisely dimensions of irreducible representations of Thompson on the nose. And likewise, the subleading coefficients decompose into a direct sum of representations, which you can actually compute. Yeah, okay, I'll just end with that. And so here are some parting thoughts that I offer you. I'll just summarize what we've discussed. We were able to build several examples of chiral algebras whose symmetry groups are encoded by various sporadic groups. These constructions are sort of nice in that they capture the relationships between several sporadic groups by mirroring the diagram of their inclusions in a CFT setting. The methods we used seem natural and I would think are applicable more broadly in connecting group theory to physical models. And there are various open problems that I think would be interesting to get to the bottom of. For example, there are many other Monstralizers that you could hope to find commutant pairs for. And there's some of these that seem just like very easily within reach. For example, we give some hints about how the held case should go, but I think there are hints about several of the other cases as well. In the least, we think that, well, yeah, I'll just leave it at that. It would be also interesting to develop a general theory for how finite symmetries play with taking cosets. I think one thing that's sort of interesting is that, well, I've been emphasizing that this diagram of subgroups of the monster has a VOA mirror, and it's sort of functorial. Functors like that tend to arise in things like Galois theory. So in Galois theory, there's a functor from the sublattice of subgroups of the Galois group to field extensions in between two fields. And well, this sort of thing that we've discovered in a VOA setting has a sort of similar flavor. So it would be interesting to determine whether or not there's something like a kind of Galois connection, but for Cosets VOAs. And then lastly, since we're at a number theory conference, I think it's an interesting challenge to try to characterize the various vector valued modular forms that arise from these coset models. And in particular, we can ask if there's anything which distinguishes them, like the genus zero property of Monstrous moonshine, which unfortunately I didn't have time to tell you about today, but perhaps you'll hear about it in other talks in this conference. Okay, and that's basically all I had to say. So thanks very much.
So thank you very much, Brandon. Are there any questions? Please feel free to unmute yourself and ask Brandon.
Then I have a question. So you mentioned the house duo and the theta correspondence in passing, and in the meantime, you also can compute the characters for the CFT, these pairs, and so presumably you can. There is a corresponding mathematical statement like a theta correspondence that you start with the theta functions and then kernel and integrate, you get the other functions. So the question is that you get the two characters for the two parts related with the W and W tutor. Are they related by the theta correspondence or something like that?
So I'm not terribly familiar with the theta correspondence, but well, they are related in a Chiral-like fashion in the sense that they sort of, I mean, there is just a correspondence between representations of, say, the icing model and representations of the baby monster CFT. They just appear next to each other in the decomposition. I did mention I was trying to emphasize only in passing, you're right, the fact that these Monstralizers are dual pairs. I sort of wanted to speculate that, for example, if you look at this set of characters here, the leading coefficient is irreducible on the nose. And I sort of wanted to say something like, the reason this happens, which it doesn't need to happen in general, I wanted to say that the reason this happens is because we're working with a dual pair of subgroups of the monster. And if you tried to take a coset that didn't preserve a Monstralizer, then you wouldn't see this. And in fact, all of the examples that we have, the leading coefficients are irreducible on the nose. And for a few examples that we computed that didn't correspond to Monstralizer pairs, we saw that they weren't irreducible on the nose. So it's sort of tempting to speculate that the manifestation of the fact that you're working with a dual pair in the monster group is this, this fact that the leading coefficients of the characters are irreducible. But I don't know. We haven't proved anything like that.
Mhm. Okay, thank you.
Yeah, any more questions?
Yes, I have a question.
Please.
I'm sorry, perhaps I missed part of your talk, but how did you find these stress energy tensors?
By the way, I can't scroll, but is that Scott that just asked that question? Okay, great. So one way that we found them is that, we didn't find them certainly. There's just this abstract theorem which says that there's a one-to-one correspondence between Ising stress tensors and 2A elements. So that's useful in doing the baby monster example. And then there's actually work of mathematicians, which I think the relevant thing that you'd be asking about is, over here. So over here, when I say that we consider this Chiral algebra that's generated by two Ising stress tensors, that itself has another stress tensor. And that was computed, those stress tensors were computed, the central charges of those stress tensors were computed in work of various mathematicians that, unfortunately, I worry that if I try to give credit, I'll give credit to the wrong people. So, but I can link to that work if you'd like afterwards. But the rough idea is just that there's this structure theorem which says that if you have a VOA, which is generated by two Ising stress tensors, then the OPEs in that VOA are constrained so heavily that there's only 9 possibilities for what you get. And it turns out that you can compute very explicitly the space of dimension 2 operators in these theories. They're like very low dimensional, like no bigger than 15 or something. And so you can just compute idempotents in their corresponding Grice algebra and you figure out what the conformal vectors are. That's like the rough summary.
Okay, so have you done anything beyond dihedral case?
Yes, we did. So, there's a few cyclic cases here. And for example, the Z3A case, it corresponds to a central charge 4/5 stress tensor. It's a parafermion theory, Z3 parafermion theory, or you'd like the third, one of the minimal models. Likewise with this Z4A example, I actually just think that something like the following statement should be true. If you find a monstralizer such that one of, say, G, the smaller group in it, is generated entirely by 3A and 2A elements, then you can just cook up a corresponding VOA, and it's something like the VOA generated by the associated Ising stress tensors and Z3 parafermion stress tensors. And you should try to take the coset of that. So I think there's various generalizations that one could try to pursue. In particular, the held example sort of goes like that because this group 7:3, which is the dual of held, is generated by 2 3A elements. So I would expect that you take the coset of a VOA that's generated by a pair of parafermion, Z3 parafermion stress tensors, then you'll probably get a theory with held symmetry, for example.
Thank you.
Yeah, no problem.
Okay, are there any more questions? Okay, I've got one. So the first one is that, like, in the end, you mentioned that are there any properties analogous to Genus zero properties that one could study? I mean, off the top of my head, I only know Rademacher summability. Do you have anything else in mind, or?
Yeah. So actually, yeah. So by the way, in our work, we only considered the sort of identity McKay-Thompson series, none of the twines. But we
Okay.
found Rademacher expressions for all of those. So yeah, one answer could be that they're all Rademacher summable. I don't know how much. Well, it could be that that is, well, how to say. Yeah, I'm not sure in this general setting of vector valued modular forms how like unique it is to have Rademacher summable McKay-Thompson series, but that could very well be one characterization that's analogous to the genus zero property. Of course, in the monster case, the genus zero property was only later reformulated in terms of Rademacher series. Originally, it was just the statement that the invariance groups, if you quotient the upper half plane by them, lead to genus zero Rayhaun surface. But
Right.
I don't think that statement will literally be true here, probably.
Right. And did I perhaps see somewhere, maybe I was mistaken, but did I see somewhere that you had these theories which had a 2B element in this Monstralizer pair somewhere? Oh yeah, there you go. In
Yeah.
the next slide. So, well, no, perhaps the next one. Oh, it's 2.b. Okay, it's not the 2b twinning. Because I was just, you have Z2A, sorry, I just read that as Z2B. Because my question would have been that if you get a 2B element, how would you do that physically? Because those things are non-geometric, right?
Oh, the 2B case actually is sort of stupid, right? It's like,
right, yeah.
Well, I think, okay, I'm sort of trying to remember what the story we want to say is on the fly, but let's see. Okay, so if you look at the bottom of this 23, this
right, yeah, exactly, 2B, yeah.
Yeah, but you sort of, okay, so good. So the way the monster is constructed is as a an orbifold of the Leech lattice VOA. And this monstralizer here is sort of relevant to that in the sense that, what's the statement? The statement is something like this Conway 1 group sort of is like the group of symmetries that sends untwisted states to untwisted states and twisted states to twisted states. And the Z2B sort of acts as +1 on the untwisted states and -1 as on the twisted states in this orbifold or whatever. So I think the sort of, this is a little bit of a degenerate case of this structure in that I think the commutant pair you would want to consider here is like the Leech lattice VOA, rather the subspace of the Leech lattice VOA that's fixed by its canonical Z2 involution, and the trivial theory. So it's a little bit of a degenerate case, but if you go through and like consider this example carefully, it sort of has basically all the features that that I talked about. For example, the Z2 fixed subspace of the Leech lattice VOA has precisely this Conway group symmetry as an example. And okay, so this is a little bit of a silly degenerate case of our construction, in any case.
And does it make sense to ask, well, because you've got the monster CFT and the chiral 3D gravity theories. Is there any case that you can ask, does it even make sense to think of these monstralizer pairs holographically?
Yeah, I was debating. Yeah, I mean, I personally don't know. Of course, you know well that we've been seeing a resurgence of efforts to try to take like 2D theories that ought not to have a holographic dual, but sort of seem to have some kind of contrived holographic dual anyways.
Yeah.
So it's possible that these Rademacher expressions for the characters have something to do with a holographic realization, but I don't really know. As far as I know, this story with the monster CFT and its like ADS3 dual was sort of not ever very precisely.
No, it's not precise. It's just, yeah.
But yeah, I agree. It could be interesting to, yeah, revisit that with these other theories sort of in mind or something.
Yeah.
Well, I can tell you some stuff offline about potentially how cosets would be related to that.
Yeah, you tell me next Wednesday or something.
Sure.
Okay. Are there any more questions for Brandon? I don't see any hands. Okay, so I'm guessing if you do have any questions, Brandon might probably be around for certain discussion sessions, so you can probably go find them. Is that right?
Yeah, for sure.
Okay. Okay, so thank you very much, everyone. And apologies for the confusion. There was a timetable mix-up, and Jeff Harvey's talk has now been rescheduled for Thursday. So if you are here also to watch Jeff's talk, please tune in again on Thursday. And just a quick question. I've received certain complaints saying that